Hi, I am Xyrelle Agustin from ECEA 111-1 Section B10, and in this video, I am going to discuss angular modulation. Before we start the discussion, here are the learning objectives of this video. First is to discuss frequency modulation and phase modulation concepts. Then, show FM or PM signal in time domain, frequency spectrum, including its mathematical equation. And lastly, define and show equation for FM or PM modulation index, FM percentage modulation, frequency deviation for FM and phase deviation for PM, deviation ratio, FM equation using Bessel functions, and practical bandwidth calculation for FM. Now let's start off the discussion by defining the frequency modulation. Frequency modulation or FM is defined as the process in which the frequency of the carrier is varied in accordance with the instantaneous value of modulating voltage. The amount of change in frequency is determined by the amplitude of the modulating signal. As seen on the figure, the frequency of the carrier signal increases as the amplitude of the modulating signal rises as well. Frequency modulation also provides near-interference-free reception, and it was for the reason that it was used in many applications from broadcasting to communications and offers several advantages over other models. In addition to its widespread use of high-quality audio broadcast, FM is also used for a variety of two-way radio communication systems, whether for fixed or mobile radio communication systems. As per the phase modulation, as the name implies, phase modulation or PM uses variation in phase for carrying the modulation. It is also sometimes used for analog transmission, but it has become the basis for modulation schemes used for carrying data. Phase modulation is also considered similar to frequency modulation and is an important technique in digital communication systems. We have all heard of AM radio and FM radio, but phase modulation seems to be in a different category, such as PM radio is by no means a common term. It turns out that phase modulation is more relevant in the context of digital RF. In a way though, we can say that PM radio is as common as FM radio simply because there is a little difference between phase modulation and frequency modulation. FM and PM are the best considered as two closely related variants of angular modulation, where angle refers to the modification of the quantity passed to a sine or cosine function. And speaking of FM, PM, and AM, let's now compare the three. In terms of differences, these three differ in function, carrier parameter, and types. For the function of AM, amplitude of carrier wave varies as per amplitude or voltage of modulating signal input. As per the FM, frequency of carrier wave varies as per voltage of modulating signal input. And for PM, phase of carrier wave varies as per voltage of modulating signal input. As per their carrier parameter, for AM, frequency of carrier wave is kept constant. For FM, amplitude of carrier wave is kept constant. And for PM, amplitude of carrier wave is kept constant also. Now, in terms of their similarities, all these modulation types are analog modulation techniques. In addition, all the modulation types are used to transmit information from one place to the distant place. And mostly, these techniques are employed in wireless communication. Proceeding to the FM and PM signal in time domain, frequency spectrum, and mathematical equations. In terms of the mathematical equations of frequency modulation, we will write the carrier as sine omega ct. It already has a frequency, namely omega c, so we will use the term excess frequency to refer to the frequency component contributed by the modulation procedure. This term is slightly misleading though because excess implies to a higher frequency, whereas modulation can result in a carrier frequency that is higher or lower than the nominal carrier frequency. In fact, this is why frequency modulation does not require shifted baseband signal in contrast to amplitude modulation. Anyways, back to our carrier signal sine omega ct, if we add the baseband signal xbb to the quantity inside the parentheses, we are making the excess phase linearly proportional to the baseband signal. But we're looking for frequency modulation, not phase modulation. So we want the excess frequency to be linearly proportional to the baseband signal. As we all know, we can obtain the frequency by taking the derivative with respect to time of phase. Thus, if you want the frequency to be proportional to xbb, we have to add not the baseband signal itself but rather the integral of the baseband signal, because taking the derivative cancels out the integral and we are left with xbb as the excess frequency. This can be seen on the first equation. And on the second equation, the only thing we need to add here is the modulation index m. The function of modulation index in FM is that it allows us to fine-tune the intensity of the change in frequency that is produced by a change in the baseband value. In terms of the time domain of frequency modulation, let's look at some waveforms. As shown in the first figure, here is our 10 MHz carrier. The baseband signal will be a 1 MHz sine wave as follows on the second figure. The FM waveform is generated by applying the formula given earlier. The integral of sine x is minus cosine x plus c. The constant c is not relevant here, so we can use the following equation to compute the FM signal. And now here is the result. The baseband signal is shown in red. It almost seems that the carrier hasn't changed, but if you look closely, the peaks are slightly closer together when the baseband signal is near its maximum value. So we do have frequency modulation here. The problem is that the baseband variation are not producing enough carrier frequency variation. We can easily remedy this situation by increasing the modulation index. Let's say m is equals to 4, thus the equation given. Now we can see more clearly on the fourth figure how the frequency of the modulated carrier continuously tracks the instantaneous baseband value. As per the frequency domain aspect, AM and FM time domain waveforms for the same baseband and carrier signals look very different. It is interesting then to find that AM and narrowband FM produce similar changes in the frequency domain. In both cases, a low-frequency spectrum is translated to a band that extends above and below the carrier frequency. With AM, the baseband spectrum itself is shifted upwards. With FM, it is the spectrum of the integral of the baseband signal that appears in the band surrounding the carrier frequency. For the single baseband frequency, M is equals to 1 modulation, we have the following fifth figure. The next spectrum is with M is equals to 4 as shown in the sixth figure. In conclusion, this demonstrates clearly that the modulation index influences the frequency content of the modulated waveform. Spectral analysis with frequency modulation is more complicated than it is with amplitude modulation. It is difficult to predict the bandwidth of the frequency modulated signals. Moving on to the mathematical equations of phase modulation. We already know that the frequency modulation is achieved by adding the integral of the baseband signal to the argument of a sine or cosine function. This can be seen on the figure 7. As we recall, we introduced frequency modulation by first discussing phase modulation. Adding the baseband signal itself rather than the integral of the baseband signal causes the phase to vary according to the baseband value. Thus, phase modulation is actually a bit simpler than frequency modulation. The similarity between phase modulation and frequency modulation becomes clear if you consider a single frequency baseband signal. Let's say that xBBT is equals to sine omega BBT. The integral of sine is negative cosine. In other words, the integral is simply a time-shifted version of the original signal. Thus, if we perform phase modulation and frequency modulation with this baseband signal, the only difference in the modulated waveforms will be the alignment between the baseband value and the variation in the carrier. The variations themselves are the same. This will be more clear in the next section where we look at some time domain plots. And now speaking of time domain, we'll use the same waveforms that we use for the FM discussion, such that at 10 MHz carrier and the 1 MHz sinusoidal baseband signal, as we can see on figures 9 and 10. Here is the FM waveform with m is equals to 4 that we saw on the previous page. We can compute the PM waveform by using the following equation, where the signal added to the argument of the carrier wave uses positive sign instead of negative cosine. And now here is the PM plot. Finally, the frequency domain of the phase modulation. The preceding time domain plots demonstrate what was said previously. Frequency modulation and phase modulation are quite similar. It's not surprising then that PM's effect in the frequency domain is similar to that of FM. Here are the spectra for phase modulation with the carrier and baseband signals used as seen on the following figures. Lastly, on the final part of the video discussion, we have more definitions and equations. For the FM and PM index, the frequency modulation index is the equivalent of the modulation index for AM, but obviously related to FM. In view of the differences between the two forms of modulation, the FM modulation index is measured in a different way. As shown on the figure provided, FM modulation index is equal to the ratio of the frequency deviation to the modulating frequency. On the other hand, as with other modulation indices, PM index indicates how much the modulated variable varies around its unmodulated level. It relates to the variation in the phase of the carrier signal as shown on the given equation. Note that the delta theta is the peak phase deviation. Next, percentage modulation. The percentage modulation in frequency modulation is the ratio of actual frequency deviation in the FM wave to the maximum allowable frequency deviation. For reference, provided on the left is the formula and the example for the percentage modulation. Next, we have the deviation. The amount of change in the carrier frequency produced by the amplitude of the input modulating signal is called the frequency deviation. As seen on the equation provided for the FM deviation, the carrier frequency swings between Fmax and Fmin as the input varies in its amplitude. While in phase modulation, for a sinusoidal modulating wave, the phase deviation expressed in radians is equals to the modulation index. Accordingly, the deviation ratio can be defined as the ratio of the maximum carrier frequency deviation to the highest audio modulating frequency. One common example of the FM deviation ratio can be seen by taking the figures for a typical FM broadcast station. For these stations, the maximum frequency deviation is plus minus 75 kHz and the maximum audio frequency for the modulation is 15 kHz. Using the formula given, this means that the deviation ratio is 75/15 or equals to 5. Next, for the Bessel function, we'll start off with the base formula with a cosine carrier wave with frequency Fc and adding a signal with amplitude beta and frequency Fm. Now, to prove the Bessel function, we need 3 basic trig identities and 3 Bessel function identities. Starting off with the base formula and applying the sum identities for cosines, we get the following equation. Now, let's take the first term and apply one of our Bessel identities to expand it to this equation. This equation can be simplified to this equation where the sum runs over all even integers, positive and negative. Now, we do the same with the second half of the cosine sum. We expand this equation to this equation, which we can simplify into this equation, where again the sum is over all the integers, where it is add this time. Combining the two halves gives us our result to this equation, which is our Bessel function. And finally, we have the bandwidth of frequency modulation signal. The bandwidth of a complex signal like FM is the difference between its highest and lowest frequency components. and it is expressed in hertz since bandwidth deals with only frequencies. FM signal spectrum is quite complex and will have an infinite number of sidebands as shown in the figure. This figure gives an idea how the spectrum expands as the modulation index increases. Sidebands are separated from the carrier by Fc plus minus Fm, Fc plus minus 2 Fm, Fc plus minus 3 Fm, and so on. Only the first few sidebands will contain the major share of the power, and therefore only these few sidebands are considered to be significant sidebands. As a rule of thumb, often termed as Carson's rule, 98% of the signal power in FM is contained within a bandwidth equal to the deviation frequency plus the modulation frequency doubled. And the Carson's rule can be seen on the equation below. And that's the end of the discussion. Thank you so much for watching.